Okay, hi everyone. I'm doing the timing issues on 5324. And basically, if you look at timing, timing is very important. We always take it for granted and assume that the operations are going to be synchronized using a clock. And in this set of slides, we're going to look at the clock and see can we do without it. And basically, if you look at a clock basically does two things. One is to make sure that you don't have any, hazards and race conditions. And the other thing that it implicitly does is it controls the order of operations. So when in a microprocessor, for example, you have a set of instructions running one after another, basically you're implicitly ensuring that if an instruction requires the results of a previous instruction, that happens. And of course, I mean, in advanced architecture, you're going to see topics like out of order execution and so on. So that requires more sophisticated hardware to detect what kind of dependencies you have and change the order of the operation, and it still make the program run as if you're running it exactly in the order of the instructions that the compiler or you as a user have determined. Now, there are two problems with clock. One is the fact that the assumption that the clock signal, which is a global synchronization signal, is not going to arrive at all the destinations at the same time. And number two, the clock itself is very expensive, as I'm going to show you later. The capacitance and the power consumption of the clock is very high. So if you can avoid using a clock, that would be great. And if you remember in the intro slides, I talked about clock frequency going up and that resulting in dynamic power going up and all kinds of thermal issues and so on. So people have been talking about maybe you can run different clock domains, and at some part of the chip you could run it at say 5 gigahertz, but the bus that is moving data between memory and that functional unit could be running at 1 gigahertz. So you could run different clocks at different speeds. So these are all options that you can think about. That's called globally asynchronous, locally synchronous, and we are also going to look at asynchronous designs later. Okay, so basically when you look at the clock signal, it connects every single register and flip-flop, either in a whole chip, which used to be the old days, or a big chunk of the chip. So if you have, 5 or 6 clock domains, and in embedded systems you could have, 10, 12, 15 clock domains. And you're talking about approximately 1/10 of all the flip-flops in your system, which itself is a huge number. So because of that, and of course, I mean, you don't just have the registers and flip-flops. You could potentially have clocks for pre-charged logic, dynamic logic, and because of that, your clock is going to have a huge fan out, which means you have high capacitive load values. And also, in terms of routing, when you route the clock all over the chip, then it means that from the clock driver to the destination of the clock, you're basically going to take different routes with different lengths, and that means that you cannot guarantee necessarily that the clock is going to arrive exactly at the same time on all the flip-flop clock entries all over the chip. And basically what that means is that the assumptions that you're going to make in terms of timing may be violated, so the chip might fail. And just to give you an example from an alpha processor, which is pretty old, but this number hasn't changed much. So the clock network has about 40% of the chip capacitance. And that's going to be an issue by itself, but as I mentioned earlier, you do have clock skew as well, which is defined as the time difference between the same clock edge arriving at two different flip-flops. And if they're not exactly at the same time, that might cause issues. And we're going to look at how it could violate timing in a bit. Um, And of course, I mean, if you look at the clock, the clock is going to be delivered using a tree, and that tree has wires, and you could play around with the width of the wire to reduce the resistance of the clock. And for that, you would get, different sweet spots in terms of how wide the clock network has to be. So this one is again from an old technology, but the concepts are still the same. So here we're assuming that you have a source of a signal. So this could be a big buffer driving the clock signal. And then you have the RC, intrinsic RC resistance capacitance of the clock wire or clock tree, and then you have a load that the clock is going to be delivered to. And you can see here as you change the clock driver size, the timing is going to change. So on this axis you have the timing, time to arrival time of the clock, and here you're playing around with the width of that segment of the wire that is delivering the clock. And you can see that there are sweet spots, and depending on your source resistance, that sweet spot could change anywhere from here to here. So if you want to optimize, you basically have to look at all the properties of your network and so on. And it's not surprising that, a clock design could be, an 80% team that does the clock design. So it could be quite challenging. Now, in terms of the actual implementation, so as I said, I mean, if you have a bunch of combinational logic, as is shown on this slide, combinational logic 1, combinational logic 2, combinational logic 3, each with the register at the end, then you would assume that a clock phi is going to come in, and you assume that T phi prime, T phi double prime, T phi triple prime are going to be all exactly happening at the same time. But I mean, physically, the signal has to travel from here to here, and there's going to be delay in between that, right? So we want to formulate that and basically find out how much the skew can change based on the delays of the wires that are going to deliver the clock signal. So skew is basically defined as the time difference, absolute time difference from this point to this point. And if you look at every block, basically your combinational logic is going to have T logic min, T logic max. And think of it this way. Suppose that this is an adder, right? And if you have a bunch of gates in the adder, the least significant digits are going to arrive faster, right? So for your sum signal, S0 is going to arrive at the input of this register 1 is going to arrive there faster compared to your most significant digit, which is going to arrive later. So think of this TL min, TL max as the least significant and most significant bits in an adder. But it doesn't have to be an adder, right? I mean, you could have any combinational logic, and the combinational logic is going to have a vector of input and a vector output. And if you look at all the paths from the inputs to the outputs, basically you're going to have a minimum length path and a maximum length path, and these minimum maximum paths could change depending on what kind of input you have. So with the actual input value, these values would change too. And of course you have the setup and hold times, and again you could look at the worst case and best case scenarios, and that would give you TR min, TR max. And essentially what you want to have is you want to make sure that the data arrives at the right time. And by the right time, what I mean is you want to make sure that the data, the minimum, the fastest that the data can go from the inputs of the combinational logic all the way to the output of the combinational logic to be to arrive there. You want to make sure that that data is not too fast compared to the delay of the clock. Okay, so I mean, you can assume that this is for whatever reason, let's say 2 time units, and let's say the sum of these is only 1 time unit. So basically what happens is that this register is waiting there to receive the values from the previous computation, and those values are stable, they are at R2, and you're waiting for this clock edge to arrive to fetch those values into R2. But if it happens that these guys are too fast, then they could come in, override whatever values that you had here, and by the time that the clock arrives, you have lost the previous values that you never caught and never saved in R2. So this is a race condition, right? This means that your input is coming too fast and is overriding the value from the previous cycle that you never got a chance to um, uh, write. Okay, and if you think that this is an unreasonable assumption, it's really not. I mean, basically, if you look at this delta, the amount of skew that you could have on a clock could be potentially large because the clock tree that is delivering the values to this R1 could have a bunch of branches going out. So the capacitive load on this, remember Elmore delay? So the capacitance value on this downstream tree could be pretty high, which makes this value significant. And if you think about adder, again, look at the least significant bit. It only needs to go through a few gates, and it is not unreasonable to assume that you will have race conditions. So basically, if you put 2 plus 2 together, you would figure out that your delta, the amount of skew that you have on your clock, has to be less than or equal to this minimum value, right? So the no signal, no data should arrive sooner than that delta. And if you think about the maximum bound on delta, essentially what you want to have is you want to have the data fetched in this clock cycle. So let's say right now you're not worried about the fastest arriving value to the inputs of R2, but you're worried about the most significant bits of your adder, for example. And what could happen there is that at this point, the new data is released from R1, and mind that at this point, the data from the previous value was fetched into R2 and presented to the next pipeline stage. Now, during this time, your combinational logic has time to do its processing, and by this time, you want to make sure that the data is ready here, because if you have any more changes to the data after this clock goes high, and this is supposedly, the master stage of this R2, then you're going to close the gates and you're not going to fetch that value, right? So this is the parameter that you've been worried mostly, during the semester. You want to make sure that you make your timing and your latency timing constraint is honored. And essentially, if you write the equations for that, you would know that the time, from the time that you release the data, so the time that your data gets released here, that's t phi prime, and you're going to go through the logic max and register max, and TI being the wire delays, whatever wire that is connecting your combination logic to R2. You want to make sure that that time is less than or equal to this time, which is going to be time of phi prime plus t. But if you look at t phi prime, t phi double prime, it's basically going to be t phi prime plus delta. Put it on the other side of the equation, inequality, and you would get this, right? So now you have to ask the question, how are these delta values going to affect my clock period, and how they are going to affect my race condition? And one more point that I need to add is that here I assume that your delta is positive, right? So if your clock signal is being routed in this direction, right, then you would get the clock first here, and then with some delay you would get it here, right? But that doesn't have to be the case, right? I mean, your clock driver could be here driving this guy, so this could actually come sooner than the edge that you would see here, right? So in that case, we're going to say that your delta is going to be negative. Now, is your delta if your delta is going to be negative here, then basically what happens is that the delta is going to add to this part a positive number, and that means you have more slack in terms of your delay. You have more slack for your latency, and your latency is going to like a negative slack. So it's potentially going to be a good idea to have negative slack. And if you look at the previous slide, you're going to see that if you have a negative value here, this condition is always going to be honored, which means you're not going to have race conditions. So a negative delta is good for race condition. It's going to make it go away, but a negative delta is going to make your t longer, which means your clock frequency is now going to go lower. So it's bad. It's bad for your clock frequency. And I apologize. I think I misspoke. I said that it's good for T, but essentially you're increasing your clock period, which means your clock frequency is going to decrease with a negative delta. So if you think about the different values of delta, if your clock skew is positive, then basically it shortens the clock period, right? On the previous slide, you're doing some, the T logic maximum minus delta, which was the clock period. So if you have a positive skew, it's going to, in essence, trick the system, and the system is going to assume that your combinational logic has a less delay, which means clock frequency could go up. But the problem is, if you have race conditions, then you're doomed. There is nothing you can do. And essentially the system is not going to work. But if you have negative delta, it means that your race condition never happens, but that means essentially you're slowing down the system. And of course, I mean, if you have a two-phase clock, then that gives you more flexibility in moving the phases of these phi1 and phi2 clocks and get rid of some of the issues that you would have had. So in the single phase that I showed you earlier, if you had a race condition, you're doomed. You can't do anything about it. In two phase, you can fix it. So let me skim over this part. I'm not going to walk you through the calculations here. You can do it at home and essentially follow the calculations that I had, but basically what I'm showing you here is that you have phi1, and phi1 prime has a skew. So phi1 prime is the master clock of the second stage of the pipeline, and also you have the distance between phi1 and phi2. So that's the phase distance that you have between them, and that could potentially be a parameter that you as a designer could control, right? I mean, you have the you have the logic that generates phi1, phi2. You can decide on what T phi1 wants to be. You can decide on T phi12 wants to be, and basically by moving these pulses around, you can have more flexibility and fix stuff potentially. So as I said, let me skip over and show you that this basically what this boils down to is that your T min has to be greater than skew minus T phi12, and your T max has to be less than the period plus delta minus T phi12. So again, you can see that T phi12 is essentially offsetting your clock skew. So if your skew is too high, you can use T phi12. You can use a larger T phi12, the separation between the two clock phases, to counter that. And basically what this means is that if now you have a race condition, then you can address it. You can have a larger T phi12 and get rid of the race condition. The only downside to that is, of course, that by increasing your T phi12, you're probably increasing the clock period. You're slowing down the system. But it's better to have a slow working system compared to a system that doesn't work because of its skew issues. All right, and of course this is an example. Slide 13 is showing you the case in which you could have both positive and negative skew depending on the direction of the data path. So if you look at the data is moving in this direction on these logic elements, but it's moving in this direction in this part of the logic. So if your clock is going from left to right, you're going to have negative skew for these guys, but you have a positive skew for the bottom portion of it. Now, in terms of clock routing, people have different topologies, and this, begins to get into computer-aided design topics. That is, given a source of the clock, a main clock driver, how would you route the signals to all of these registers to get them at the same time? And there are two major structures for clock design. One is what is called H-tree network, which is shown on the left. And essentially, if you look at it, so if your main clock driver is here, you would get to this point, and then both of these points are symmetrical. So basically, whatever width of the wire of the clock tree you use is going to be the same on these two. And then if you look at it, all these points are getting the signal exactly at the same time. And of course, I mean, I'm assuming here that you're not dealing with any process or thermal variations here. But if you ignore PVT, then every single flip-flop that is shown in this structure is going to receive the clock exactly at the same time. So it's as if your skew is zero. Now, this could be expensive because, I mean, you might have congested regions in the chip. Maybe, let's say, this part of the chip is already congested with a lot of signal routing resources, so you may not be able to do an H-tree design. Another alternative would be what is called a comb tree network. And essentially what you have is like the football goalpost, and right off the bat, you would know that the clock signal is going to arrive here earlier than here. And also you would know that this signal here is going to get its clock value earlier than these guys. But if all of this is within an acceptable range of clock skew, then you're probably fine. And it's reasonable to assume that a clock, basically this register, which is going to receive the clock very late, is not going to communicate with this register, which is going to receive the clock pretty early. If they do, then maybe you need to move them closer to each other or do some other techniques to make sure that the clock arrives early on. And if I want to show you an example, DEC alpha, again, old chip, but we do have the data. And here you can see the chip micrograph, and it shows you the clock drivers. And the next slide shows you the amount of skew that you have. And obviously, I mean, if you look at the center, you have a zero skew because that's where your clock drivers are, and then you could have pretty high clock skews here. But a high clock skew in itself is not necessarily bad news, right? If you look at the floor plan, basically you had some of the logic that does the floating, well, not floating, but ALU operations and stuff here. And then this part is part of the cache, and you have cache controllers here and so on. So none of these ALU units, for example, your adder unit is not going to directly connect to your cache line and get values from that memory, right? The memory is going to first go to the memory controller, and then you have your sense amp or whatever that you need to have, and then going from there to there. So the important point is within one clock cycle, the neighboring or the units that exchange data, they have to have low skew. But if over multiple cycles you're going to fetch the data from cache, sending it to the cache controller, and then in the next cycle you're sending it to a register, in the next cycle from register to your adder, the cumulative skew between these could be really bad, but if consecutive cycles are okay, then the chip is going to work. All right, so now let's turn to the question of self-time. Can we get rid of the clock signal altogether? And the answer is yes. There are things that you can do, of course, with an overhead to completely get rid of the clock signal and ensure sort of explicitly in control logic that the operations are going to be performed in the right order. So if you look at clock, basically clock design, um, take an adder for example, right? In an adder, you're going to look at the worst case scenario. You're going to say my carry propagation is going to go from bit number 1 all the way down to bit number 64, and that is the worst case scenario. It might happen just 1 in a billion, but because it might happen, it means that your clock period has to be long enough to accommodate for that, right? But on average, you're probably going to be, running a 20-bit carry propagation, so it seems to be an overkill. Now, truly asynchronous design, I'm not going to talk about. People do use it in some memory um, applications in which you have a regular architecture and you could basically have a dummy row that transfers data from a memory cell to the bus. And if you set that to be a representative of your worst case delay in your memory array, then you can rely on that to tell you when the read operation is done. But I'm not going to talk about that anymore. We're going to talk about self-timed design, in which you don't have any clock signals, you explicitly create some handshaking signals so that each unit would tell the next unit, I have the data ready for you, start doing the computation on it. And it's basically going to boil down to an average delay of a circuit, and as a result, it's going to become faster. So basically, if you look at a combinational logic, a pipeline design, now here I'm showing you 1, 2, and 3 combinational logic elements, and then we have these handshaking units on top of each combinational logic. So remember, no clock is there. And basically what happens is that each unit has to receive the start signal. So start is going to tell it, you have the data ready at your input, start doing the computation. And then once the combinational logic is done doing its computation, it has to send a signal saying, I'm done, right? And that's not enough. You have to have some coordination between these handshaking stages. So basically each handshaking handshaking unit is going to send a request for computation. It would say that, my combinational logic has done its job. It has data ready for you to be processed. And if the next unit is not going to be ready anytime soon, that means that this unit is not going to accept input from its previous unit, right? So it has to be sort of handshaking each unit, waiting for the next unit to receive its data before it can process new data. So whenever the next unit is ready to process the data, it's going to send an acknowledge signal telling them, yes, I'm okay, I received the data, you can go ahead and process a new batch of data. So I'm going to show you just the animation, which says, a request came, and then this unit 1 said that, yes, I'm not busy. I acknowledge immediately that I did receive the data at R1. Right? So when request comes in, it means that new data is ready. Can you fetch it or not? So acknowledge here means, yes, I was available. I did fetch the data. You can go ahead and process a new batch of your own. And basically it will say to CL1 that, you know what, R1 has new data, you can start processing. And CL1 has to do number crunching, and after a while it has to generate this done signal. And remember, this done signal is not set in stone. It depends on what kind of data you're dealing with. So if you have an addition operation which only has 2 bits of carry propagation and after that you're done, the done signal should be generated much faster than when you have 64 bits of carry propagation. And once that happens, your handshaking signal would like to get rid of the data that is stored in CL1. So it will send a request saying that I have data for R2. And if the next unit is not available, maybe it's still processing what is on the CL2, then it may not give you an acknowledged signal, which means if a new request comes in, this HS is not going to send an acknowledge. Okay, so you wait and you wait and you wait, and you potentially will have a backlog of data before CL1, and once CL2 is ready, it will send an acknowledge, and of course it will fetch the data in R2, and it will tell the combination logic to start doing computation. It sends a done when it's done, and so on and so forth, right? So a lot of things could be happening at the same time. You could be CL3 could be doing its computation. CL2 might be sitting there idle because CL1 is busy, but once CL1 is busy, once CL1 is done, it could immediately send the data to CL2 because CL2 was available and process the data. So you think of it as a bunch of bubbles moving through this, and the bubble speed could be, higher or lower depending on where you are, but on average you're going to get a faster throughput of data through the system compared to a very rigid synchronous system in which your clock system is always set to cater to the worst possible scenario. So let me, walk through this fast. So basically the issue would be here. Number one, you get rid of that clock signal with the huge capacitive load and, a lot of power consumption. So you throw that out, which could bring down the power consumption of the chip significantly. And you can potentially get a much more increase in performance because now you're dealing with the actual speed that the system needs, right? As opposed to the worst case scenario, always being paranoid about, losing data. And of course, as a side note, so techniques such as Razor, these are techniques that allow you to speed up the system and not worry about the worst case scenario. So in Razor, you could potentially set your clock speed to be close to the average, maybe a bit slower, and then assume that most of the time you're going to be fine, except the cases that you're taking longer, and then Razor is going to figure out that, I had a timing violation, so it's basically going to stop the system, maybe run it for another cycle, giving it 2 cycles for this operation to finish, and that way you can address the same issue. That's why Razor is really an important work. It allows you to basically bridge the gap between asynchronous and synchronous designs. Now, the disadvantages of asynchronous is that it has large area because those handshaking signals do need some logic to implement. And also you need those start and done signals to be generated by the combination logic. But people do use it, so it's pretty useful. And a way that you can implement the start and done signal is to use dual rail. And I think you've seen dual rail in 5323. And essentially what you do is for each signal, you're going to have a B0 and a B1. And if it's 0, 0 means that it's in transition, and only one of them is going to become 1 after you're done doing computation. And by design, you'll make sure that this never happens. And in that case, then, your done signal would basically be the OR of B0, B1. Whenever any of them becomes 1, you know that the computation was successfully done. It's similar to, doing pre-charge logic. You would know that, if you pull down the output, you know that the computation is done. Except that in the regular pre-charge logic, if the signal remains at 1, you don't know is it the pre-charge value that is remaining the same, or was it the evaluation was done and I decided to keep the pre-charge values. So what you end up doing is that you end up implementing the function as pull-down network, and you would have the pull-down network bar. You would do the complement of the function to ensure that at least one of PDN and PDN bar is going to go low, and that way you ensure that you always know when the computation is done, and you don't have to wait for that, pre-charge value. Is it done and evaluated as one, or is it still doing the evaluation? And I'm looking at the pre-charge values. So you can see that immediately your pull-down network is doubling in area because you're implementing both PDN and PDN bar. But generating PDN bar is not going to be that difficult, right? I mean, De Morgan's law, and if you just, invert every input and, change series, which is the NAND implementation, to parallel, which is the NOR implementation, you'll be done. And at the end, you get your done signals. So this is the network. And, in the past, I have asked the students in final exams to generate pull down and pull down bar network and show all individual transistors in it. So be prepared to do an example in this one. And note here that the inputs also double because you have input bar for every input that you had. In terms of the output, if you really think about it, B1 and B0 are the output and output bar. So if once you start doing the implementation using this technique, and if you need to cascade a bunch of these logic elements, you already do have B bar as the output, so that could feed into the next logic. So we figured out how to do the done signal, and your start signal could basically be the footer and the pre-charge signals that you have that, whenever a start is asserted, basically you start doing computation. Whenever it's not one, you're basically doing the pre-charging. And essentially, yeah, I think I did talk about this. One important point is in the previous slide, we only had one bit B0, B1. But if you have an n-bit adder, you have to OR all of them because you want to make sure that every single one of those sum signals is done before you tell the next logic that it can go ahead and fetch the value. So this is an example Manchester carry chain, and here is the original circuit that we had, and here is the pull down network bar. Note here that we didn't change the topology in this particular example. Usually what you do is you apply the Morgan law and then you change all the parallel connections to series connections. And what I mean by parallel and series connections is that these guys are in series. In the complementary network, these would be parallel. These guys are parallel. They will become series. I'm sure you've done this in 5323. So just a reminder. But in this particular case, we did use our knowledge of the workings of the adder, and essentially what we did was we didn't change the topology. We just changed your generate signals with the kill signal, and also the C, intermediate C signals now become C bar signals. So basically this, if you look at this implementation and if you write down the equations, the Boolean equations for the two networks, you can verify that these are indeed the top and the bottom circuits are implementing carry and carry bar. And if you look at the done signal, here you can see that I'm ORing C1 bar to make sure that C1 is evaluated, but I'm ANDing all of these to make sure that every single one of these C signals has been evaluated, and that means that I'm done. Okay, so basically if you look at this design, if your carry is going to be generated at every bit position, then instantly you're going to have your C1, C2, C3, C4 evaluated, which means the done signal is going to be raised immediately, right? But if you have a long propagation, then your C4 is not going to evaluate until you have propagation through the whole thing, and that's going to give you the fastest method. And I know what some of you are thinking right now. Some of you are saying, well, why can't I just take C4, C4 bar and eliminate these guys and use C4, C4 bar as my done? Isn't that the critical path? And the answer is no. pause the video, think why that's the case. All right, now I assume that you got it because it could be the case that for one particular input combination, you could have a kill right here, which means C4 is going to be generated immediately, but you might be in propagate mode, which means your C3 is going to be generated much later than your C4. So the answer is you cannot get rid of these guys. You do need every single one of them to make sure that all your carry signals from this block is ready before you can proceed to the next step. And here, of course, I'm assuming that you're using this logic to and the next pipeline register is going to fetch all the S values or all the intermediate C values in computation. If the only output that you have is going to be C4, yes, then you can do that. You can only take C4 and use that as the done signal. But if you are doing all the intermediate signals like what we did with carry select adder, in which you needed the vectors of carry intermediate carry signals to just combine them with an XOR with the S signals, with the AND signals to get the sum, then in that case you need to AND all of these. So it's all context dependent, and you have to see what inputs are being fed to the registers, and you have to have the done signal for those, for all of those signals that are feeding the register, the pipeline register. All right, so just to give you an example of the implementation, and this is, again, the technology in which this was implemented doesn't matter, the relative numbers do matter. So in the self-timed version, you had about 0.23 nanoseconds per bit, which was the same delay as your synchronous, but you used more area, slightly more area compared to synchronous because of all the handshaking signals and PDN, PDN bar, and so on. But in terms of actual performance, you got order log n delay. Right? Remember the Manchester carry chain? That was n divided by 4, which was linear, right? And I said that in order to get log, you needed to go to those expensive Brent Kong, Kogi Stone, tree-based adders. But here you can use a simple linear implementation and use essentially use self-timed technique to get an average log n delay, which is amazing. And of course, I mean, again, in terms of worst case delay, you're still going to be n, but that worst case doesn't happen too often, so you can do much faster implementation. And then the other issue, so we looked at the start and done implementation, how you can do that using dual rail, and now we have to talk about handshaking protocols. And basically in the handshaking, you want to make sure that you're avoiding race. If the next unit is not ready, don't shove the data down its throat. You have to wait for it to basically be ready for the data. And also you want to make sure that you're avoiding hazards. You want to make sure that you really wait for the done signal from your unit before you tell the next register pipeline that it can fetch the data. And there are multiple ways of doing the handshaking. And basically what you do is you use state machines to essentially provide this handshaking and coordinate the operations. And usually the type of operations, the type of signals you need to transmit, and I'm not necessarily meaning, I don't necessarily mean that you have to have 4 explicit signals, but you need to convey these 4 events here. The sender has to say, I have a new data available, and go ahead and fetch it in your register. It could say, I request that you do computation on it. Now these two could become potentially one signal, and then your receiver has to acknowledge the receipt of the data, and also it has to say, I'm ready for new computation, send the data so that I can fetch it. Again, these two operations could potentially be combined into one operation. So the simple handshaking would be the 4 phase handshaking, in which you have a request and an acknowledge between the sender and the receiver, and you have data, right? And of course, I mean, the picture is not, quite complete here, but let's work on this simplified example. So basically, and the reason this is called four-phase handshaking, because if you look at the values of the four phases, you could have 0, 1, you could have 1, 1, you could have 1, 0, and 0, 0. So these are the four phases that you would have. And here the cause and effect are shown by these red arrows and the dashed purple arrows. And essentially what happens, sorry, let me go back. Sorry, I had a glitch. So here basically what happens is that your uh, you get an acknowledge from the receiver here, and that acknowledge is going to tell the sender that it can send the data. And of course, I mean, when you think about these handshaking events, don't just think about the pipeline event. I mean, you could potentially have a data buffer here, and maybe you're talking about a network on chip. It could be anything, right? And a data transmission could take some time, and it doesn't necessarily have to be just one data sent to a register. And once you receive the data, and you finish sending the data, you would request the data to be processed, and that's what the sender is going to do. So the sender is going to say, data is ready, I'm going to send a request to you. And the receiver probably is going to receive the data and do computation on it. So it's going to basically acknowledge, once it receives the data, it's going to acknowledge that, yes, I received the data, I'm doing the computation on it, and the buffer is empty. You can go ahead and load the data on it again. And once you acknowledge, oh, sorry, no, the data cannot be written. So here, basically, during this time, your receiver is doing computations on it. And once it's done doing the computation, it's going to raise this acknowledge, which says, I'm done with the data. You can dump new data into the buffer that we have between us. And that is going to start a new cycle. How do you implement it? Usually people use what is called the Muller C element, which has memory. And the reason it has memory is that in order to proceed, you have to have the sender to have new data, and also the receiver has to be free. So the sender and the receiver go through the phases of locking the Muller C element and unlocking it so that it can send and receive data. So basically what happens is that when the Muller C element, which is, as I said, a sequential, and it could be implemented using this method or this method, it's static or dynamic logic, is that when A and B are 0, your F, the output of the Muller C, is going to be 0. When one of them changes to 1, it's going to maintain its existing state, and when both of them become ones, then it changes the state to 1. Okay, so if both are at 1 and only one of them changes back to 0, then Fn is going to remain at 1 until both of them are ready to be 0, and it changes the state to 0. So let me stop here. I think I can finish the rest of the slides in class. So thank you.